My name is YORDAN PAUNOV. I'm also a PhD student of Professor Alexandrov in Lakehead University and Technical University of Sofia as well. And what I'm going to present today is investigation of the ratio parameter for optimization of LENR. On short, because already Professor Alexandrov showed the experimental design, but really quick, we have constant on wire wired around an aluminum rod. We use roughly the same diameter and the same length for the constant on wire to avoid confusion. We use pure deuterium, 99.95% purity, and an aluminum rod, roughly 1 centimeter in diameter is the aluminum rod, 1 meter of the constant on wire with diameter of 0.3 millimeters. So the background for my study. As you already saw, we have multiple successful experiments. They are reproducible. We have results in every experiment we do. We have reproducibly seen excess heat in all of them. And also helium-3, helium-4, 3 helium deuteride, and 4 helium hydride with the RJ here. In previous works, we have proved strong helium heat correlation to provide a proof for the nuclear origin of the reaction. So my study does not comprehend on that, but it tries to get to the next phase of it. Once we have it, we try to optimize it. So what we initially tried was with different temperatures to get a temperature parameter investigation that could give us the best initial temperature for the experiment. In here you can see that article is also published. You can see the temperature experiment we have done with 3 initial temperatures of 510, 527, and 535 degrees Celsius. Again, that's the temperature of the whole specimen with the parameter. The temperature of the constant on wire is in around 670 degrees, between that and 700, and up to 950 when we want to break stuff. And what we see here is we not also have higher average temperature, but what we tend to do is have a higher temperature between peaks. So as you can see in here, we have a high peak and a low value after the deuterium is injected, and we have a lower between the peaks. We have a lower temperature, as in the 535 degrees. We have not only a higher average temperature, but we have a higher temperature here between the peaks. For the optimization, we are also using KI, as my colleague provided the explanation of it. And for this study, we are trying to investigate the ratio between injection versus no injection ratio. That's what I mean by the ratio. So the problem statement, as you can see here, we have around 8 seconds after injecting the deuterium, we have this low value here, this drop that we want to remove. That is because the deuterium is injected at room temperature and is cooling the whole specimen. That is temporary until the reaction starts and we see an increase in the temperature again. This yellow line here shows the initial temperature of the specimen. That is showing that we have heat generation at any point in time above the initial temperature that we have. So ideally, what we want to achieve is remove that drop and have a more stable peak value. The goals of that is to improve the reaction stability, to have a more stable reaction, as I said, without transients. We need to minimize the cooling effect and, of course, increase the total energy output of the system. What is the approach we have tried here? So for this specific experiment, we are avoiding preheating of the deuterium. That is a subject of something that we are planning to do at a later stage, but at this point, due to safety and technical limits, we want to avoid it. So we then modify injection versus no injection ratio in order to remove that drop, and then we study the impact on the thermal behavior and the impact on the reaction stability of that. So the first injection ratio we tried is 1:1. It replicates the previous experiments, and here we see that the drop is still present, still observed, so nothing changes in this one. And we tried with the 4:5 ratio. We see similar behavior. Even in this ratio, we see a drop for a very short period of time below the initial temperature, but it's only for a short period of time. Actually, even I think my line is not quite right, so it might be even above. And on the last one we tried, 11:7 ratio. As you can see, in here we have a more stable profile. So we have a temperature drop of only 10-15 degrees of the whole specimen compared to the 35-40 of the whole specimen with the previous ratios. We had a very much more stable profile on this one, and we have a higher peak-to-peak value. And it's not completely reduced, the drop. We have in some cases where it's completely reduced, but for this one it's not, but it gives us a little higher peak, so that's the best one in the average also. So I decided to provide this one. This is the result summary. As you can see, the difference in the temperature of the whole specimen, it's around maybe 35 degrees, and we have a much more stable profile without this drop here, which is what we're trying to achieve. We want to have stable heat generation. That way we will have in a reactor we'll have predictable heat, which will remove the option for something to break, fail, etc. because of a drop or a peak of heat generation. And a reasonable conclusion we can do is that with the injection ratio, we can control the transients, we can reduce the cooling effect, And from all the three we tried, 11-7 provides the most stable temperature, stable structure. What we plan to do from here is to investigate the transmutation in the constant time wire. We could do that with a specimen that has evaporated and the one that has not. We can also use the suggestion that was provided earlier to check the alumina rod. For transmutations, we plan to do further ratio and temperature research to get to the point we want of the more stable temperature and the best energy yield, and also improvement of the calorimetry is what we could do better, in my opinion. This is the pictures of the Constantan wire, as again no plasma is used. And I would gladly answer any questions if present. And thank you very much for your attention.
So this session is open for questions.
Yeah, one over there.
Question quite simple. I didn't see in the previous presentations, what's your decop?
Sorry?
Decop.
The COP is 4 to 16 again. That's what Dr. Alexandrov presented. It's
4 to 16.
Yeah, 4 to 16 in our experiments. For this one, 11-7, the ratio. That's not. We have not done exact for that one, but I think probably around 6 or 7 on that one, maybe more. For this one, we haven't. That's something that, yeah, we'll do for sure. But it's not been below 4 from all the experiments we've done. So.
Okay, this question to you and Alexandrov. So, did you try to use again wire after the experiment several times, cycling?
We have changed the wire if it evaporates.
No, yes, but without.
The experiments we do it the same wire over and over and over again.
Yeah, did you try?
Yeah, we do it like this. We don't change it after each experiment. We do it with the same over and over and over again until we break it.
Also in the regime of evaporation?
No, that's something that's interesting. By the way, we could evaporate it, then get a smaller part of it, and yeah, or maybe evaporate a bit higher. Yeah, that's something we could try.
What happens with other types of wires? I don't know. Is it possible to think a wire as a blank? I don't know, an iron wire or whatever else?
Can you do blank with another type of?
Yeah,
with another type of wire.
Yes. What happens with the nickel wire, iron wire? There is a wire that is not active at all and doesn't give trace into, for instance, spectroscopy of any kind.
I think. I'm not sure on that one. Maybe Dr. Alexandrov can.
So we can do this one. The reason that we are using constant on wire is, in fact, there are two reasons. First of all, general reason is Dr. Celani provided very nice results. Had very nice results. It was actually the first motivation. The second reason was that actually constant noise is relatively cheap. $5 for 50 meters. So, and it works. Okay, I assume that if we change the specimen, let's say wire, we maybe, let's say, use platinum, palladium, or something like that. Maybe you see, the goal will be the temperature, initial temperature, because in order to get these things, we have to heat the wire, initially heat For constant wire, we must heat at least for 500 degrees Celsius in order to get this kind of effects. Below doesn't work. I can provide the corresponding information about this one. We must heat. So now, this is the first thing. So for the goal will be, if we use other specimen, other wire, will be to decrease this actual initial required heat in order everything to begin. However, if we use, let's say, platinum, palladium wire, it may work, it may not work. I don't know. But for sure, the cost will be significant of creation of the specimen. But constant works, by the way.
It doesn't work.
No, I mean, I have a solution cheaper. Put hydrogen instead of deuterium and see the difference.
So now, we tried with hydrogen. Generally speaking, for this circumstance of experiments, we don't have energy release. However, I'm saying however, if we increase, there is a way to increase the amount of hydrogen in the wire. It is crucial condition in order to get effect. However, the increase of the amount of hydrogen wire will not come from increase of the pressure. There is another ways. But it requires the change of the experimental scheme. So it's with something like that. For now, we don't have plans to do experiments with hydrogen. This one reason. For another reason is actually we cannot store hydrogen and deuterium in the same room together. It is a thing. One tank only per room.
Thank you. Any other question? No? Thank you very much then for your talk. Thank you. Is there